The environment beneath, around, and inside a hurricane has a major influence on how strong a storm can become. To visualize three of these influences, let's use North Fort Myers Community Pool as a backdrop and step inside a brand new NBC2 animation. Influence number one, water temperatures. A key ingredient for hurricanes to form is warm ocean water. If you think of the pool here as being the ocean, once the water gets to at least 80 degrees, a significant amount of heat is released into the atmosphere when the water from the pool, or in our case the ocean, evaporates. You can see this in action. When air rises, it cools and condenses into showers and downpours and thunderstorms. And the heat that it's pulling from the surface of the ocean helps to give things like tropical waves an extra kick. An important place to watch is here in the Gulf of Mexico between Cape Coral and Cancun. The Gulf Loop Current often holds some of the warmest waters in the entire Gulf thanks to underwater currents pulling it out of the Caribbean. This is a place where hurricanes can get very strong, very fast. Hurricane Michael in 2018 is a great example, going from a Category 2 to a Category 4 as it moved over the current. Influence number two, the West African monsoon. Now, if you'd use your imagination for a moment, pretend that the pool deck here is Western Africa and the pool is the Atlantic Ocean. When this tropical wave right here moves off the western coast of Africa, it's able to get stronger the moment it hits the ocean because it's tapping into the energy that it's pulling from the warm waters below. Now, on years when the West African monsoon is more active, there's simply more tropical waves moving over top of Africa, hitting the Atlantic Ocean. This increases the odds that at least one or two of these tropical waves will find the perfect environment suitable for strengthening. Influence number three, eye wall replacement cycles. A major wild card in hurricane forecasting is accurately predicting when an eye wall replacement cycle is going to start and how long it's going to last. Take a look. Now, if we were to generate a giant hurricane over top of the pool here in North Fort Myers, we can get an idea as to what an eye wall replacement cycle might look like. These only happen in really, really big hurricanes over top of warm bodies of water like the ocean. Now, this hurricane, as you can see, is really, really well defined. See how clear-cut that eye happens to be? At the same time, though, this hurricane is likely tapping out on the maximum amount of energy that's available to it in the atmosphere. When this happens, a new ring of thunderstorms tends to form around the original eye wall. And eventually, this new secondary ring of thunderstorms will take over and become the new eye wall. During this cycle, the hurricane tends to get wider, but it also temporarily gets weaker. And that's why timing is so important. Last year with Hurricane Idalia, the storm weakened from a Category 4 to a Category 3 just before making landfall, because just before it made landfall, it started an eye wall replacement cycle. Now, this process can last anywhere from a few hours to more than a day. And despite all of the advances in modern weather forecasting, it is still very, very difficult to get an idea as to exactly when a cycle is going to begin. Reporting local from North Fort Myers Community Pool, I'm First Alert meteorologist Rob Duns, NBC2. All right, and we're from our inland areas, which of course can experience significant flooding during a hurricane. Let's move our attention back to the coastline, of course, when it comes to the risk of storm surge flooding. I want to show you a map. This is a really important map for you to understand if you live in Florida. It's called a bathymetry map, and what it's basically showing you is what the surface of the earth looks like underneath the surface of the water. On this map, areas that are shaded in dark purple indicate very deep water. Areas that are in red are relatively shallow water. Look at how far off of our coastline you have to go to find yourself in very deep water. Now compare that off the coast of, say, Broward County, where the water gets very, very deep, very, very fast. This is referring to something called the continental shelf, and this is a major reason as to why our part of Florida is so vulnerable to storm surge. Another way to visualize this is to look at these clay models. So if you take a look at this side here, imagine this is off the coast of, say, Fort Lauderdale. If we were to pull all of the water out of the Atlantic Ocean, you'd find a very, very steep drop-off to very deep water. This offers areas of Broward County natural storm surge protection that the water can't get over as quite as easily. On the other hand, on our coastline, if you pulled all of the water out of the Gulf of Mexico, look at this. You'd have a very slow and gradual drop down to deeper water. This is why storm surge is more easily pushed on shore in shallow water and why it's harder to move on shore during deeper water. So if you want to truly understand our community, you have to look deep beneath the surface of the water because that plays a big part of the story. Thankfully, with this Hurricane Ernesto business in the Atlantic, we are not concerned about storm surge here locally. But with the check of what's going on with that storm and what's happening in the backyard, let me send things back into Fort Myers with Chief Meteorologist Allison Ray. Let's take a moment and help you visualize one of the biggest wild cards of any given hurricane season, the Saharan air layer. Now, with this, the name says it all. This is a dry and dusty air mass that originates here from the Sahara Desert of Africa, the biggest on the entire planet and oftentimes, of course, the hottest place on planet Earth as well. Now, to represent the sand of the Sahara, we're going to use these mounds of brown sugar. And to represent the steering winds in the atmosphere this time of the year, we'll use this small fan. Now, because there's so much sand and dust both on the ground and in the air here, it gets pushed toward the ocean because of the winds. And NASA says that in any given year, some 60 million tons is actually moved around. Now, oftentimes, the highest concentration is where you see here off the west coast of Africa. But of course, every once in a while, you'll get a high enough concentration of it for it to impact the weather, even as far away as where we are here in Florida. Now, you know when the Saharan air layer is nearby here in Florida, because oftentimes we have super vibrant sunrises and sunsets. The sky looks very milky during the afternoon, and we oftentimes have little to no thunderstorm development even on hot and humid afternoons. Now, it's tempting to think that the weather plays out like you see it on TV on a flat map, but that's not the case at all. Get into the thinking that weather happens vertically, three-dimensionally, and the Saharan air layer is a great example of that. Instead of imagining the Saharan air layer moving directly over the ocean, you should imagine the Saharan air layer moving aloft. It's upwards sometimes of 20,000 feet. Remember, this air mass is originating from the Sahara Desert, so it's very warm. As it moves over top of the comparatively cooler ocean waters, because warm air likes to rise, it is lifted upward. And because there's so many pieces of sand and particulate matter inside the Saharan air layer, it is absorbing the sun's energy, and that keeps this layer of the atmosphere warmer than other layers around it. Now, of course, the Saharan air layer isn't the only thing that comes our direction from Africa during hurricane season, as you are well aware of. We're also very closely watching something called the West African monsoon. That is when little clusters of thunderstorms form over Africa just to the south of the Sahara Desert and also move toward the ocean with the prevailing winds. Now, as the Saharan air layer tends to spend a lot of its time up around 20,000 feet in the air, when these tropical waves try to fire thunderstorms, if they're underneath an environment with a lot of dry, dusty air, that can greatly take away their potential for development. Some tropical waves completely fall apart, other ones struggle to make it across the ocean. But of course, every once in a while, a tropical wave will find the sweet spot, if you will. It'll move off the west coast of Africa, and if it's able to thread the needle and move in and out of the Saharan air layer, those are the tropical waves we have to watch the most, because they have the best opportunity for forming into an eventual hurricane as long as it has plenty of warm ocean water and favorable upper-level winds. Our community is surrounded by water, and everything you see around you basically falls in one of three categories. You have fresh water, which would be what you find in something like Lake Okeechobee. You have salt water, which is what you'd find, of course, in the Gulf of Mexico. And then you find something we refer to as brackish water, which is essentially a combination of fresh and salt water. You find it most often when you have like a freshwater river run into a saltwater body of water. Now, as long as these three categories of water stay separate, the environment is totally fine. But hurricanes have the ability to greatly change the composition of water when storm surge events are unleashed on land. You can picture it this way. If you think back to Hurricane Ian and areas that were hard hit by storm surge like Pine Island and Sanibel Island, a lot of freshwater ponds that weren't connected to the Gulf of Mexico before the hurricane were overrun with saltwater flooding, saltwater flooding will be represented here by this blue foil. Now, of course, eventually the saltwater retreated, but the thing is, is the salt that was inside that water stayed in the freshwater ponds. So now, post-hurricane, we can't consider them to be freshwater, but instead would refer to them as being brackish water. Now, there are some animals like alligators and bull sharks that can go back and forth between fresh and salt water without a problem. But a lot of the things like freshwater fish and frogs that would have normally been inside your freshwater pond, since the hurricane, have probably all died out. So if this applies to you in your community, you're probably thinking to yourself, well, when is everything going to go back to normal, right? Unfortunately, it's going to take quite a bit of time. To visualize this for you, what I did here is I put a whole bunch of salt water inside this bowl. So think of this bowl essentially as being one of those ponds that's now turned brackish. During the dry season in South Florida, it's not at all uncommon for the water to almost entirely evaporate out of these ponds. But because salt is a solid, it is left behind in the environment. So how do we get rid of that salt? It is a very slow process. Even though it might take a hurricane only a few hours to cause a body of water to go from fresh to salt, it can take years and years and years of flooding. If you think of the water inside this watering can as being freshwater rain flooding, you have to literally physically flood the area year after year after year to physically remove the salt in order for the environment to go back in balance. Hang in there.
At least here at our office, we've never had it pop during the fill-up process.
Comforting words from National Weather Service meteorologist Stephen Shively as the whooshy sound of hydrogen inflates an increasingly gigantic weather balloon.
Because these balloons are very flexible. You'd be amazed when it's windy how they can contract and expand.
The data he'll collect in the next 2 hours with this balloon is very valuable, especially when a hurricane is threatening. Its payoff comes in collecting data through a profile of the atmosphere that helps us determine if, when, and where a hurricane may track, even if it's far away right now.
If you watch these systems, you know, they go from the lower altitudes to what we call the mid-latitudes. And that turning point where those trade winds curve, a lot of these storms curve right around Florida, and when they start to turn, that's when they start to slow down.
That's because hurricanes are steered by winds around them, not inside them. So, if steering currents are weak near us, pay attention.
We need to find that weakness too, and we need to figure out, because wherever that weakness is where the hurricanes are going to go.
Here's how the process works. Shively starts by cutting off the hydrogen supply when the balloon grows to about 5 feet across. Then he ties it using a nearly 250-foot-long string.
I was excessively tied up.
A small parachute is attached before he moves indoors for the most important part, the radio sonde.
So this little tip here, that's the temperature sensor.
Radio sondes are little instruments telling us big things, like the temperature, wind, and pressure of wherever the balloon may go. This small green light signals when it's ready to roll. Back outdoors after Shively connects it to the parachute, he's kind enough to let me do the honors.
5, 4, 3, 2, 1.
The moment that balloon is released, it gets to work. While we watch it shoot into the sky with our NBC2 drone here, the data it's collecting appears on Shively's computer screen here, showing us in near real time what the atmosphere looks like. It's also sent as input data into weather forecast models that run trillions of math calculations with it in only a few hours' time.
A model is only as good as the data that's going into it.
And weather balloons get lots of it. Dozens are launched nearly simultaneously from coast to coast each day, many going upwards of 100,000 feet, expanding up to 20 feet across before they pop. That's when that parachute, by the way, deploys and the radio sound floats back to Earth.
We have a lot of great technology that does a lot of great, I would say, guesstimations, but nothing is as good as actual good old-fashioned just measurements.
So the next time a hurricane threatens our area, listen for when extra weather balloons are launched out west, because the information they gather on the inbound steering currents could signal when a storm may turn away from us or move right toward us. Reporting on the road in Ruskin at the National Weather Service, I'm First Alert meteorologist Rob Duns, NBC2.
That was a beautiful shot, wasn't it? Now, if you think about how that weather balloon rises higher and higher in the sky, another key important point in hurricane forecasting is those weather balloons can help to give us an idea as to what amount of wind shear happens to be present in the atmosphere. As you should know, if you live in Southwest Florida, hurricanes don't like wind shear. It makes it very difficult for them to organize. And if a hurricane runs into an area with stronger wind shear, oftentimes that storm will weaken. A way to visualize this is to think of a snowman. In order for a snowman to stand up, it has to be stacked vertically. It can't be tipping over to one side or the other in order for it to stand up. So if you think of a situation where we have strong wind shear, picture the top of a snowman basically tipping over like that. When a hurricane encounters strong wind shear in the upper parts of the atmosphere, the hurricane can get sheared apart and oftentimes will completely fall apart. On the other hand, though, if a hurricane encounters an area of weak wind shear, there's less force pushing at the top of the hurricane, or in our case, a snowman, which allows that hurricane to get stronger. It's important to remember here that the amount of wind shear a storm is going to encounter will change from day to day. And that's why it's, of course, important to stay up on the forecast with the latest. If you think back to 2022, at least in its infancy, Hurricane Ian struggled a lot with wind shear. But as the hurricane got closer to our area, the wind shear was weaker, and that's why the storm got stronger. Thankfully, with Ernesto, the current hurricane we're tracking in the Atlantic Ocean, we don't have to be at all concerned about its issues locally. But as it moves toward an area of weaker wind shear, it looks like the island of Bermuda will have a lot to watch over the next several days. So for a check of the tropics and what's happening in the backyard this afternoon, let me send things back into the studio with First Alert meteorologist Justin Hobbs. Justin. You know, over the years, I've been very fortunate to work with a lot of our community's schools at teaching our area's kids about the weather. So for this Hurricane Week segment, I wanted to make something kind of geared towards your kids and your grandkids to help explain a pretty complex subject, and that would be the subject of storm steering. It is the steering currents around a hurricane that basically tell it where to go. Whether it moves right toward Florida or bends before it gets anywhere close to land, it's these storm steering features that play a really big role in determining where a hurricane is going to go. Something important to remember when we talk about this topic is to remember that the intense winds within a hurricane are not the winds that push it across the ocean. Instead, a hurricane almost has to be told where to go by winds that are outside the hurricane, pushing it in one direction or another. Kids, a way to think about this is to think of a toy like a spinning top. You know, if you were to throw a spinning top on the table like this, they will spin and spin and spin and spin and spin, and they'll spin for a long period of time, but they really won't ever go anywhere unless you physically push it in one direction or another. That's why hurricanes are somewhat similar to spinning tops, in that they can generate a lot of spin with themselves, but unless they're physically pushed in one place or another, they're never ever going to really move in any one direction. That is why another toy you can think about that helps explain this concept of storm steering is something your grandparents might be a little more familiar with, and that would be a marionette puppet. A marionette puppet is a puppet that is steered from up above, just like a hurricane in many respects. Now, if this puppet's going to do anything, the only way it can do anything is by being told by the controllers up above to move its arms or move its legs or to physically walk across the table. Here's how it's like a hurricane. A hurricane can be very, very tall. In some cases up above 45 or 50,000 feet. And it's the winds in the upper parts of the atmosphere that can push on a hurricane and push it in one direction or another. So just like our marionette puppet here, if the winds are very strong in the upper parts of the atmosphere moving that way, they will physically push the hurricane just like a marionette puppet is controlled from up above. So when it comes to hurricane steering, what you want to listen for with mom and dad and grandma and grandpa would be things like the Bermuda High, trade winds, and cold fronts, because those all act as steering features, just like the controllers of a marionette puppet, to push whatever we're forecasting to move in one direction or another. Reporting in the studio with little Rob Duns. I'm First Alert meteorologist Rob Duns, NBC2. Back to you. Though storm surge and wind cause the most amount of damage when a hurricane makes landfall, another threat you can't ignore is the potential of spin-up tornadoes, especially out and ahead of when a hurricane makes landfall. Tornadoes are generated by something called wind shear. That's a phrase that represents how the winds change as you move higher in Earth's atmosphere. To help you visualize this concept, though, I built this little contraption here. Now, there's really two types of wind shear. The first type is called directional wind shear. It refers to when the wind is moving in different directions in different levels of the atmosphere. The second type is called speed shear. That refers to when the winds are moving at a faster speed the higher in the atmosphere you go, and that's the type that's most important to focus on when a hurricane is making landfall. If you think of this piece of paper as representing the wind, when you have a concept of speed shear in place, faster moving winds in the upper parts of the atmosphere encourage the air to almost do a somersault on itself and generate a horizontal rotating column of air. Now, when a hurricane's nearby, if it happens to get caught up in one of the storm's updrafts, that horizontal column of air turns into a vertical column of air that we would refer to as a tornado. The wild thing is that hurricanes generate their own wind shear as soon as they start moving on land. When a storm is over the water, there's less friction between the hurricane and the surface than when the system begins moving on land. This drag and resistance it meets when making landfall slows the wind down in the lower part of the storm while the upper level winds keep up their speed. But pay attention, because not every part of a hurricane produces tornadoes equally. To find the area of greatest concern, you have to look for what's called the dirty side of the hurricane. To find it, look at the storm from above. Note the direction it's moving and then draw a big plus sign. It's here in the right front quadrant where tornadoes are most likely. This part of the storm tends to have the most winds with a hurricane, and because this is when onshore winds move on land first, that's where you'd find the most internal wind shear capable of spinning up tornadoes. Now, Hurricane Ivan in 2004 caused the most number of confirmed tornadoes by one tropical system. Of the 120 that hurricane spawned, 18 of them happened right here in Florida. Reporting local in Fort Myers, I'm First Alert meteorologist Rob Duns, NBC2.
Have you ever heard that saying that it's good to think outside of the box? Well, that may very well be the case when it comes to hurricane forecasting. Let's talk about the concept of A-bear boxes, an idea from the late Paul A-bear of the National Hurricane Center. Back in the 1970s, A-bear noticed that a lot of major hurricanes that went on to make landfall in South Florida happened to move across two specific parts of the ocean. One here just east of Puerto Rico and another one here in the Western Caribbean. Now, it's important to say that this is just an observation, and there have been plenty of hurricanes that have moved through these A-bear boxes which have not impacted us in Florida, and other storms that have gone outside these boxes that have brought some really big impacts to our state. But from our community's local history, there have been some awfully notorious storms that have lived up to the idea. Irma and Donna both moved through A-bear box 1. Ian and Wilma both moved through A-bear box number 2. So though this concept isn't anything official, history shows us that if a big storm is on the prowl, we're better off if it goes outside the box.